Hi everyone, this video is about prefix-free codes and the Kraft-Macmillan number. You might recall from the previous video that a code is uniquely decodable exactly when its extended code function is 1-to-1. Another way of saying that is that we're always able to, with certainty, decode encoded messages. That is, if we start with a message in our original alphabet and then we encode it and give it to someone else, that someone else should then be able to recover the original message with certainty. Now, it can be hard to tell directly whether a code is uniquely decodable. So what we want to do is to link unique decodability to a characteristic of codes that's easier to check. So that characteristic is the characteristic of being prefix-free. So a code is prefix-free if no code word begins with another code word. All right, at the bottom of the slide we have some examples. And so for each of these codes on the alphabet XYZ, we're going to determine whether they're prefix-free and whether they're uniquely decodable. So in part A, notice that code word Y, that is this 0, 1, the code word associated to Y, begins with the code word associated to X, namely 0. So this is not prefix-free. Nor is it uniquely decodable. Because let's suppose I wanted to encode the message XZ. Well, if I do that, that becomes 0, 1, 0. But if I were just to hand you 0, 1, 0, that could be decoded to XZ, but it could also be decoded to YX. So this code is not UD. All right, now how about the second code? So there, each of X, Y, and Z are sent to code words of length 2. Now in the previous video, there was an example at the end where I asked you to think about whether codes whose code words are of some uniform length are uniquely decodable. And in fact, they are, right? Because all you would have to do in this instance is to take whatever the coded message is, block it into groups of 2, and then you'd be able to read off what the original message is. So this is uniquely decodable. And because all of the code words have the same length, one code word can't begin with another code word. So this is both UD and PF. Okay, so we've handled parts A and B. Now, what about for part C? Well, again, we can see that this is not prefix-free. Right? For instance, the code word 10 begins with 1, and in turn, the code word 100 is a multiple offender, right? It begins not only with 1, but it begins also with 10. So it's badly not prefix-free. But if you think about it for a little bit, this code is uniquely decodable. The reason for that is, let's suppose there's a coded message like, 1, 1, 0, 1, 0, 1, 0, 0, and you wanted to decode that message, that is, find the original message in terms of X's and Y's and Z's. Well, all you would have to do, that every single new code word begins with a 1. and that no ones appear anywhere else in any of the code words, right? So all I would have to do is every place I see a 1, I make, sort of a division here. I divide out or partition these symbols based on where the 1s occur. And so this message would have to then be X, Y, Y, Z, and there's no other choice for what it could be. So that's not PF, but it is UD, uniquely decodable. So what we're going to want to show eventually in this video is that if a code is prefix-free, then it must be uniquely decodable. But one thing we've seen in this example is that the converse isn't necessarily true, right? That if a code is not prefix-free, it can still be uniquely decodable. Eventually, we're going to show that prefix-free codes are uniquely decodable. So that makes prefix-free codes important, and we would like to be able to construct them. So constructing them in general seems like it might be pretty difficult. However, for binary prefix-free codes, these are codes, remember, where the coded messages consist of strings of zeros and ones, that any binary prefix-free code is going to correspond to a binary tree. And if you want to pick off the code words in the binary prefix-free code, you just peel off the leaves of the binary tree. Now, it could be that you have little or no experience with binary trees, so let's do a little example where we form a prefix-free code from a binary tree. So binary tree, what do? Well, you start with a single node called the root node, or the primary root node. Now from there, from that node, you can either move left or move right, or do both, or do neither. So in this example, we have both moved left and moved right from our primary root node right there. Now, when we move left, we add a 0 to the label for that node. So since we don't have any label originally with the root node, this first node in the in the next level on the left will be labeled with a 0. If we move to the right, we label with a 1. So now we repeat that process. Like from the node labeled 0, we can again move down and to the left, down into or down and to the right, or we could do neither of those. So in this example, we're doing both. And whenever we move to the left, we add another 0 to the existing label. So here, this is going to be labeled 0, 0. This one would be labeled 0, which it inherits from the node above it. And then since we moved right to obtain that node, we add a 1. Okay, now moving to the right portion of the tree, we have this node labeled 1. We move down and to the left. That node will inherit a 1 from the node above it, and because we moved left, we label it with a 0. And here, since we moved down and to the right from a 1, we label that as 1, 1, 1. Okay, now we move to a third level. Here, from the node 0, 1, this one right here, all we did from there is move down and to the left. Right? Remember, we can either move down and to the left, we can move down and to the right, or we can do both, or we can do neither. So here we move down and to the left. It inherits the original string 0, 1 from the node above it, and then you add a 0 to the end because you moved to the left. Right? And similarly, we have these nodes labeled 1, 0, 0 and 1, 1, 1. So that's a binary tree. And if we want to make a prefix-free code from that, what we do is we just pick off the leaves of this tree. So the leaves are these terminal nodes at the very bottom of the tree. So notice we have this code consisting of 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1. Those are our code words. And a code constructed like this will always be prefix-free. Now, at the bottom, we have this question. In an attempt to create a prefix-free binary code from a binary tree, why shouldn't we consider root nodes in addition to leaves? Well, remember that every single root node, like for instance this 0, 1 right here, that 0, 1 is going to be a prefix of anything that appears below it in the tree, right? And so since our goal is to avoid prefixes, we want to make sure that we avoid any root node that descends, of course, that descends to some other stuff. So in this example, we're going to use binary trees, as we suggested on the previous slide, to create prefix-free binary codes. Now, for use in this example, we're going to let n sub j denote the number of code words of length j. So in item 1, we're going to construct a prefix-free binary code where n sub 1 is equal to 1 and n sub 2 is equal to 2. So how should we do that? Well, remember, our binary tree begins with an empty node. We can move down and to the left or down and to the right, both or neither. So let's move down and to the left. We label that node 0, and we'll move down and to the right and label that node 1. Now I know that I need a single code word of length 1. And so one of these symbols, 0 or 1, needs to be chosen. So why don't we choose 0? Now the remaining code words can't descend from 0 because 0 would be then a prefix, right? And we don't want prefixes. So we need to descend from 1. If we descend from 1, we can go to the left to form 1, 0, and we can descend to the right to form 1, 1. Now if I look at those two code words, those are two code words of length 2, and that fulfills the requirements that we needed, right? So here is the desired code, C equaling 0, 1, 0, and 1, 1. Now we could have just as easily, when we first descended from the empty node, we could have selected 1 as our code word of length 1 and then found the other code words by descending from 0. So the code that we produce using this method is not unique. Further, this code would serve to encode an alphabet with 3 objects in it, like say X, Y, and Z. All right, so now let's go down to item 2 here. Here we require 8 code words of length 3. So that means we're going to have to descend quite a bit in order to obtain these code words. So let's first go to the left to get a 0. We'll go to the right to get a 1. Then we descend again to get a 0, 0. And descend again to get a 0, 1. And a 1, 0, and a 1, 1. Remember that when you descend to the left, you append a 0. When you descend to the right, you append a 1. So now let's keep going. So we get 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and then finally 1, 1, 0, and 111. And look, those are 8 code words of length 3, arising as leaves of a binary tree. Now, if we had replaced this 8 with a 9, we would be in trouble, right? We would not be able to produce a code because there do not exist 9 leaves on any binary tree at the third level. So in any case, here's what our code looks like. It's 0, 0, 0, 0, 0, 1, and it's all of these things up through and including 1, 1, 1. So here we carry on, as we did on the previous slide, in creating prefix-free binary codes using leaves of binary trees. So in our first challenge, we want to produce a code that has 3 code words of length 2, 1 code word of length 3, and 2 code words of length 4. So we start our tree at the top with the empty node. We have a 0 and a 1. We'll go to the left and to the right. So there are no code words of length 1, so we don't select either one of those nodes to be part of our code. And then we can continue on and do 0, 0, and 0, 1, and 1, 0, and 1, 1. Now we need 3 code words of length 2, and we can do that, right? So let's just select 3 of these. So here's 1, and here's 1. So we're going to select those. Now we need a code word of length 3, and that the code word we select cannot descend from any of the nodes we've previously selected. It has to be descended from this one that's unselected. So this would be 1, 1, 0, and 1, 1, 1. Now we need a single code word of length 3, so let's pick one of those. And then finally we need 2 code words of length 4. And those code words must descend from the 1, 1, 1 node. So it'll be 1, 1, 1, 0, and 1, 1, 1, 1. So we can select both of those. And so the code is 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1, 1. So that's our prefix-free code for item 1 here. So now we move on to item 2. And what happens is you'll draw a picture, maybe a little bit like the one we drew for item 1. But the problem is that if you just try on this, you're not going to be able to produce a prefix-free binary code with these parameters. And so that sort of raises a question that will be of some importance to us here, and that is, well, just because someone lays out a collection of parameters, we don't necessarily know that there exists a prefix-free binary code with those parameters. So it would be nice to have some sort of condition that told us when such a thing exists. The method of using binary trees to produce prefix-free binary codes can extend to other types of codes. In this example, we're going to construct a prefix-free ternary code. So ternary stands for 3. And we're going to do that using a ternary tree. So we're looking for a code with 7 code words. which means that we're going to look for a ternary tree with 7 leaves. Well, let's just try to produce one. So in a ternary tree, we can go left, label that 0. We can go directly down, label that 1, and we can go to the right, label that 2. And then we can continue to go down. So we don't have enough leaves yet, so we continue to descend in some way. So why don't we do this? So we can go this way to get 0, 0. And this way to get 0, 1. And this way to get 0, 2. And maybe we'll come down here and do a 2, 0. Now we still don't have enough leaves, but we can descend again. So let's descend from 0, 1. So we get 0, 1, 0, 0, 1, 1, and 0, 1, 2. And at this point, I think we've got enough leaves. So here, this is a leaf, that's a leaf, that's a leaf, that's a leaf, that's a leaf, this 1, that's a leaf, and this is a leaf. So our code looks like this. So it would be 1, 0, 0, 0, 2, 2, 0, 0, 1, 0, 0, 1, 1, and 0, 1, 2. Prefix-free codes are important because they are uniquely decodable, and we're going to verify that fact on this slide. So we start with a code, C, from an alphabet S into strings on an alphabet T. Now you might remember from the definition of a code that this function has to be one-to-one. Now for a code to be uniquely decodable, we require more. We require that the extended function, which we also denote by C, from strings on S to strings on T is also one-to-one. So let's suppose we have a couple of words in S star, and let's suppose that they give the same encoded string over in T star. Then if this code is going to be uniquely decodable, we want that to force W and V to be exactly the same message. Okay, so let's suppose C of W and C of V are equal. Well, remember that to encode a word like W or V, what we do is we encode each alphabet object, X1 through Xn and Y1 through Yn. So if C of W is equal to C of V, then that means that this concatenation of C of X1 through C of Xn has to be equal to this concatenation here. Now, since C is prefix-free, we know that C of X1 has to be dead on equal to C of Y1, because otherwise C of X1, either C of X1 would begin with C of Y1, or C of Y1 would begin with C of X1, and that can't happen in a prefix-free code. So that means that these two guys right here, C of X1 and C of Y1, have to be dead on equal. Now, because the original code function up here must be one-to-one, that tells us that X1 is Y1. So then that leaves us with the concatenation C of X2 through C of Xn equaling C of Y2 through C of Ym. And then we repeat this process once again because this code is prefix-free. we are able to conclude that these two code words must be the same, because if they're not, then one must begin with the other, and that just can't happen. And then again, because the original code function is 1-to-1, this tells us that x2 is equal to y2. And so we just keep proceeding along these lines. We've shown that x1 and y1 are the same, and then x2 and y2 are the same, and then we just keep going until we get to the end of the words w and v. And so we have then established that w and v must be the same word. So on this slide, I'd like to show you a fairly famous example of a prefix-free code. So in a simple form, Morse code is a code from our ordinary alphabet to strings on T, where T consists of these three symbols, so the dot and the dash and the pause. So here I have some exercises that might be fun for you to do and will be instructive, right? So to look up Morse code and decode some messages. You'll be asked why Morse code is a prefix-free code. And then in the last two problems, you're asked about a scenario where you eliminate the pause symbol from Morse code. So I encourage you to do this problem. Now that we know that prefix-free codes are uniquely decodable, it will be important to be able to construct them for various parameters. But the thing is, how do we know a prefix-free code exists for a given set of parameters, n1 through nm? Remember, on a previous slide, we had an example where we gave some parameters, and it appeared to be impossible to construct the prefix-free code associated to those parameters. So to help us know whether a prefix-free code with certain parameters exists, we're going to use this thing called the Kraft-Macmillan number. So if the alphabet T is of size B, then the Kraft-Macmillan number is formed from the parameters n1 through n sub m by just taking n1 over b, n2 over b squared, up through n sub m over b to the m, and adding all those numbers together. Now, oftentimes we're going to be using this Kraft-Macmillan number in some special circumstances, like for binary codes or for ternary codes. So for binary codes, the size of the alphabet T is equal to 2. So it would be the number of code words of length 1 divided by 2 plus the number of code words of length 2 divided by 4 up through the number of code words of length capital M divided by 2 to the capital M. Right, so this is for binary. And ternary is similar, right? So we're looking for the number of code words of length 1 divided by 3 now, up through the number of code words of length capital M divided by 3 to the capital M. So one thing I guess that we have not yet discussed about these parameters is if you add them all together, what does it tell you? So you might pause the video and think about it for a little bit. So it turns out that this is just the total number of code words. Okay, another way to say that is that it is the size of the initial alphabet S. Right, so that's two different ways to describe what that sum is equal to. All right, so in succeeding slides, we'll want to to know what this crazy Kraft-Macmillan number is going to do for us. Here we compute the Kraft-Macmillan number for binary codes. So in our first example, N1 is 1, so we take 1 over 2. Remember, in this case, B is equal to 2 because the code is binary. And then plus 2 over 4. And when we add those together, well, we get 1. So in the next example, N3 is equal to 8. And so all the other parameters are equal to 0, and we get just 8 over 2 cubed, which is 8 over 8, which is again equal to 1. Here in part C, N sub 2 is equal to 3, so there are 3 code words of length 2. And 1 code word of length 3. And 2 code words of length 4. And when we add those all up together, again we get 1. Now for the bottom one, we get 1/4 plus 5/8 plus 3/16. And if you add those up, you'll see that that is 17/16. Now, if these parameters look familiar to you, they should, because remember, we attempted to produce prefix-free binary codes for all of those parameters. Now, in parts A, B, and C, we were successful. But for part D, we were unable to produce the prefix-free binary code. Now, you might notice that in all of A, B, and C, the Kraft-Macmillan number is 1 or less, whereas in part D, the Kraft-Macmillan number is a little bit bigger than 1. And that's going to turn out to be sort of an important dividing line for the Kraft-Macmillan number. Less than or equal to 1 versus bigger than 1. So indeed, we do have a theorem that says that if the Kraft-Macmillan number is less than or equal to 1, then a corresponding prefix-free code does exist. So below on this slide, we have a discussion in the case that B is equal to 2. That is for binary codes. So let's imagine we're trying to form a code, prefix-free code from a binary tree. So we start with our root node, and we go to the left, 0, we go to the right, we have 1. We see there are 2 available code words of length 1. Now, N sub 1, which is the number of code words of length 1, that is less than or equal to 2, because otherwise this Kraft-Macmillan number K would be bigger than 1, and we know it's not. We're assuming it's less than or equal to 1. So we are able to select N sub 1 code words of length 1. In fact, in this example, let's suppose we're just going to let N sub 1 equal 1. Okay, now once we've done that, there are some unselected code words of length 1, and any future code words are going to have to be descended from that unselected code word, or the 2 minus N sub 1 unselected code words. So if we go down, so there are 2 minus N sub 1 of these unselected code words, and each one of those descends to 2 objects, right? So each of the 2 minus N sub 1 unselected code words of length 1 gives rise to twice that many available code words of the next length, that is of length 2. Now, since the Kraft-Macmillan number is less than or equal to 1, it's required that n sub 1 over 2 plus n sub 2 over 2 squared be less than or equal to 1. And if you do a little bit of work with this inequality, that is, if you isolate n sub 2 in this inequality, you will find that that forces n sub 2 to be less than or equal to 2 times 2 minus n sub 1. That means that we are able to select n sub 2 of the available length 2 code words, right? Remember, this number right here, this 2 times 2 minus n1, that is our available number of length 2 code words. We can't select any more than that. The Kraft-Macmillan inequality forces our number of length 2 code words, though, to be fortunately less than this number. And so we will be able to select n sub 2 of the available length 2 code words. So now, if you proceed, what you will find then is that there are this many. Actually, there are going to be 4 minus 2n times n minus 1 minus n sub 2 unused code words of length 2, and then those descend to twice as many unused code words of length 3. And then examining this inequality, if you solve it or isolate n sub 3, you find that n sub 3 is indeed less than this available number of length 3 code words. So we are indeed able to select that number of length 3 code words. And so you go on in that fashion where at every step, this inequality plays the role of telling us that we do indeed have enough code words of each given length so that we can select the desired number. On this slide, we have a few more problems about prefix-free binary codes and the Kraft-Macmillan number. I suggest that you do these problems, so pause the video and do some of them, or all of them. Part D is maybe the most challenging one on this list. On this last slide, we summarize what we know at this point. At this point, we know that if the Kraft-Macmillan number is less than or equal to 1, then that implies the existence of a prefix-free code with the given parameters, n1 through nm. But then we saw a little bit earlier that every prefix-free code is uniquely decodable. So that in turn implies the existence of a uniquely decodable code with the given parameters. So this is a chain of implications, and what we would like to know now is, well, what do we know if k is bigger than 1? At this moment, we don't know anything about what happens if k is bigger than 1, and that will be the subject of the next video.